Hi everyone, this is Mustafa Istanbullu. I am working as an assistant professor in Biomedical Engineering Department at Çukurova University. Now I am going to talk to you about an ANN-based, artificial neural network-based impedance measurement system actually for human skin impedance range. This is the content of the presentation. We will start with a brief introduction. We are dealing with impedance measurement, so I will introduce a little about the impedance measurement systems. In this study, the AD5933 impedance analyzer is utilized, so I will give you some basics of this impedance analyzer. We also used artificial neural network topologies, so exponential fitting with the least square methods, multi-layer perceptron neural network, and our artificial neural network solution to impedance measurement section will be explained. In order to test our system, we need to set up hardware and collect some data. I will show you the electronic circuit of the system also. Finally, the presentation will be finished with the test and conclusion section. Let's start with this slide. High precision impedance measurement is a widely utilized method from a biological cell analysis to a fuel cell test maybe. The impedance measurement is a simple, useful, and powerful method for the electrical characterization of cells, tissues, and the other materials. Since stable and robust high precision impedance measurement in a wide frequency range is a complicated task, the traditional instruments are generally bulky and very expensive. In some cases, for biomedical fields, of course, such as skin cancer, regular tracking of skin impedance may visualize the treatment effectivity. Daily high precision impedance measurements give some information about the abnormal tissues. A simple, compact, and low-cost impedance measurement system can be used by patients for regular tracking of that abnormal tissue. Improvements in semiconductor technology and embedded systems enable to produce smaller, cheaper, and portable single-chip impedance measurement devices. High-precision single-chip network analyzers such as AD5933 is such an impedance measurement device with direct digital synthesis and digital signal processing abilities. An impedance spectrometer fundamentally consists of a waveform generator, a voltage source, and a current measurement unit. AD5933 is a high-precision impedance converter that includes all of these units, as shown in the left-hand side figure, the blue one. The stage containing DDS core, direct digital synthesis core, digital to analog converter, we call it DAC, and amplifier is called as transmit stage. In the transmit stage, the DDS core generates 27-bit numerical sample and converts it into an excitation voltage by digital to analog converter with a 12-bit resolution. Excitation signal with user-defined peak-to-peak voltage value is applied to the test impedance connected to V-out and V-in pins. The stage connected to RFB and V-in terminals is called as receive stage. The receiving stage acquires the current from the unknown testing unit to perform analog signal processing. It digitizes the results by the onboard analog to digital converter. Finally, the discrete Fourier transform is processed by the onboard DSP engine. The DFT algorithm returns a real and imaginary data pair for each measurement frequency. The right-hand side figure shows the flow chart of the impedance measurement process with AD5933 impedance analyzer chip. The AD5933 chip considers scaling factor of the system to obtain high precision impedance measurement. The scaling factor calculation is given here in equation 1. Here, FCs and RCAL are scaling factor and calibration impedance of the system respectively, whereas the MAG is magnitude of the impedance to be measured. The recommended impedance value for the calibration of the impedance analyzer chip is defined as in the equation 2, where the Zmax is the maximum value of the impedance to be measured, whereas the Z-mean is the minimum value. Any unknown impedance can be measured by using this equation 3. Although there are many successful applications and studies with AD5933, the most significant drawbacks are the nonlinear calibration requirement and measurement error due to these calibration effects. Direct digital transfer of the measurement information constitutes an estimation problem related to analog part of the AD5933 from DDS to the DFT modules. Thus, a calibration step must be performed before each measurement to acquire the gain factor. The gain factor is used to determine the unknown impedance. The value of the calibration resistor depends on the expected range of the unknown impedance. Theoretically, the closer calibration resistor to test material impedance, the more accurate measurement provided. Here, any measurement system utilizing artificial neural networks is presented to obtain high precision impedance measurement by using AD5933 with a single fixed calibration resistance. The ANN-based solution to estimate the high accuracy impedance value includes a unique ANN topology, artificial neural network topology. The topology consists of generally two main parts. The first part realizes the radial basis function, based regression, where the second part is a multi-layer perceptron neural network with error back propagation learning. In the first part, the Euclidean distance calculation layer is followed by summation and normalization layers. All real and imaginary measurement data for a single frequency are applied to the two particular neurons at the Euclidean distance calculation layer. Also, a single summation and normalization layer neuron is assigned for measurement in each frequency. Euclidean distance calculating neurons with exponential activations also have weight values to relate real and imaginary inputs of each frequency. The least square, we call it LS algorithm, is utilized to calculate weight and exponent multiplier terms of this layer. In this study, the two-term exponential function model is used in the LS algorithm to fit the data as given in equation 4, where here AI, BI, CI, and DI are coefficients of the model, whereas mag-I is the magnitude of each RE and imaginary data as expressed in equation 5. Thus, the error function is defined as in equation 6. The smallest error can be obtained by solving the partial derivative of the error function given in equation 6 with respect to each variable. The obtained A, B, C, D coefficients are used for the preprocessing step of the artificial neural network part, as shown in this figure. In the second part of the topology, neural network topology, the correlation steps takes place in order to realize mapping from inputs to outputs. The backpropagation learning algorithm of the MLPNN, multi-layer perceptual neural network, is implemented in the second part. Although the stages are connected sequentially, they are trained independently, actually. The target value of each stage is required impedance output. After the utilization of the first stage, the data are applied to the second stage for better error minimization. In this study, two-term exponential function approximation and a modified MLPNN with additional range arrangement neurons are hybridized. The two-term exponential function approximation part used in the LS algorithm to generate the MLPNN input data is given in equation 4 in the previous page. The proposed ANN structure is shown in this figure. The structure contains, as you see, 6 layers. The first 2 layers are assigned for the realization of the two-term exponential function. These 2 layers are in the first stage. The last 4 layers generating the second stage are assigned for modified MLPNN realization. In the first 2 layers, the magnitude of each real and imaginary pair is applied to exponential function after multiplication with BI and DI constants. Outputs of exponential function units are multiplied by AI and CI constants before summation. The summation is divided by a normalization parameter, let's say N, capital N. The operations of the first and second layers are given in equations 5 and 4, respectively, in the previous section, I think. After these operations, inputs of the MLPNN parts are generated by merging the first layer and the second layer outputs as shown in equations 7 and 8. For I equals to 2, 4, and 6, the index I represents the neuron numbers of the third layer, where they are enumerated from 1 to 6 in ascending order. The net calculations of the third layer are given in equation 9, where the J is equals to 1 to 9 and Bj is the bias value. At the next step, all net J calculations are applied to the logarithmic sigmoid activation function as shown in equation 10, where the Uj is the output of the, let's say, third layer. After the activation function, the inputs of the fourth layer are obtained. In the next layer, the outputs of the fourth layer are separated into 3 groups. Each group accepts the 3 successive outputs of previous layer neurons for the net calculations as given in equations 11, 12, and 13, where the K is equals to 12, and BK is the value, BK is the bias value, and DC1, DC2, and DC3 are distance coefficients calculated as given in equations 14 and 15 and 16 respectively. At the next step, all net calculations are applied to the logarithmic sigmoid activation function as given in equation 17 to obtain the fifth layer outputs. Finally, output y, referring to the MLPNN estimation, is achieved by completing the sixth layer operation as given in equation 18. According to the backpropagation algorithm, the error is calculated as in equation 19. Error is equals to t minus y, where the e is the instantaneous error expressed as the difference between the target and the estimated output t. In the standard backpropagation learning algorithm with gradient descent, weight updates and other steps are done as in the equations given from 20 to 28. Now I won't explain each step of this section to use the presentation type efficiently. But at the end of the story, this approach is applied until the third layer of the proposed artificial neural network. The weight vectors and bias parameters of all the neurons are updated until the mean square error goal or the maximum number of iterations are achieved. This is the ANN artificial neural network training algorithm flowchart that I have been talking about. Let's continue with the hardware setup. In this study, the impedance data acquisition is performed between 1 kilo to 200 kilo ohms interval at the frequency range of 10 to 100 kilohertz. Totally 1,930 impedances are measured in the specific impedance and frequency range for training of the neural network. After 10 repetitive measurements of each impedances, the average value is taken to form the dataset. Additionally, 1,900 impedance measurements, of course, they're apart from the training data, are collected for testing the system. The left-hand side figure shows the flowchart of the data collection procedure. Impedance measurement circuits with the AD5933 impedance analyzer is shown in the top right figure. The measurement system is supplied with 3.3 volts DC voltage and internal clock with 16,776 megahertz frequency is defined as the system clock for the impedance analyzer chip. The control of the impedance analyzer chip is done by Atmega 328P microcontroller on the serial I2C communication. 16 megahertz crystal oscillator is used for the microcontroller. Two 10 kilo ohms pull-up resistors are wired to the chip to keep the serial data and serial clock pins from floating. The voltage gain of the programmable gain amplifier, let's say PGA, and the output's excitation voltage is set to X1 and 2.2 volts peak to peak respectively. A 10 kilo ohm resistor is chosen as a fixed calibration impedance. After connecting the unknown impedance to the V in and V out pins, the measurement result is displayed on the LCD screen as soon as the completion of execution. The printed circuit board PCB photography of the measurement system with annotated blocks is given in the bottom right figure. The proposed impedance measurement system is tested in the range of skin impedance values between 1 kilo ohm and 200 kilo ohms, as I said before. The test accuracy for the system is supported by using the high precision through hole thin film conformal coating silicon resistances with 0.01% tolerances. The proposed neural network has 3 specific range adjustment parameters as given in I think previous slides in equations 14, 15, and I think 16. They split the full measurement range into 3 distinct parts by considering the value of the input magnitude. All these range separations are automatically done during the calculations. Training of the proposed artificial neural network is performed by using all train data in the range of 1 to 200 kilo ohms. Thus, by calculating distance coefficients, the range of the impedance to be measured is pre-estimated. Then, the proposed neural network calculates the high precision impedances. Each testing impedance is evaluated in the related range of artificial neural network. The mean square error training curve of the proposed artificial neural network is shown in the top left figure. On the other hand, the bottom left figure gives the regression curve of the A&M with full measurement range. A significant relationship between target impedance and neural network estimation is observed as shown in this bottom left figure. In the right-hand side figure, the estimation error percentage of the proposed neural network-based measurement system for each test impedances are shown. The error percentage are given in 3 ranges to simplify the visualization. The top right figure indicates the measurement errors in the 1 to 10 kilo ohms measurement range, whereas the middle right and bottom right figures indicates the 10 to 100 and 100 to 200 ranges respectively. As seen in these figures, the maximum error is less than 1.63%, whereas the average error is 0.206% for the full measurement range. Additionally, measurement accuracies of the system and pure AD's 5933 chip-based measurement system are also compared. 10 kilo ohm fixed calibration impedance is used during the comparison for both measurement systems. Although high accuracy measurements are obtained around 10 kilo ohms, the measurement error of pure AD 5933 chip-based system increased up to 7% with respect to the correct impedance values. As seen in this figure, the average measurement error is 0.1% for the our system, our proposed system, whereas it is 2.1% for the pure AD 5933 based system in the full comparison range. This comparison range limited by the pure AD 5933 high precision operation is between 1 kilo ohm and 2 kilo ohms. The A&N artificial neural network utilized measurement system not only eliminated the calibration requirements for each measurement, but also increased the measurement accuracy considerably by applying the proposed artificial neural network-based post-processing algorithm to the impedance analyzer chip output. The comparison of the proposed measurement system with the other state-of-art studies are given in the right-hand side table. It should be noted that the studies given in the table with their reference numbers are achieved related to error rates by using numerous calibration impedances. However, in our system, obtained better accuracy measurements with a just fixed calibration impedance. On the other hand, the neural network utilization increased the processing time also, leading to a rise in the system's response time. The proposed system displays the measurement results averagely 2.6 seconds. The test results expose that the proposed artificial neural network-based system measures the impedance with the high accuracy and low cost in the human skin impedance range. The system also eliminated the requirement of the different calibration impedance usage and increased the measurement accuracy of the pure AD5933 based measurement output significantly. I think this is my last slide. Thank you for your listening. I provided my mail address and the first slide, so if you want to ask anything, you can mail me. Thank you.